Hello, my name is Orion Ning, and today I'd like to talk about my work with Ben Safdi and Welch on no evidence for superradiant axions in LIGO-Virgo-KAGRA GWTC-5 binary black hole spins. Our headline conclusion is that we derive new constraints on the axion mass, in particular the QCD axion mass, in finding no evidence for a process called black hole superradiance in the most recent LIGO-Virgo-KAGRA GWTC-5 binary black hole catalog. Here we show our constraints at 95% confidence on the QCD axion mass from this search. We illustrate our results against the axion-photon coupling GA-gamma-gamma for presentation purposes, and since we focus on the QCD axion, truncate our constraint just above and below the QCD axion band. Though our analysis does not involve GA-gamma-gamma directly and also applies to more general axion-like particles. We compare our results to existing superradiance constraints from X-ray and other LVK spin measurements, with the dashed X-ray portion indicating considerable systematic uncertainties around the high spins inferred for the X-ray based constraints. Thus, LVK searches, like those in our work here, provide a highly complementary avenue to probe these superradiance processes. The process of superradiance essentially describes that massive bosonic scalars can build around a spinning Kerr black hole and induce perturbations which then extract the spin of that black hole. These massive bosons form bound states that, under certain conditions, can exponentially build up into clouds that continuously extract the black hole spin and mass. This process is called superradiance. Formally, when one solves the Klein-Gordon equation in the presence of the Kerr metric, one can derive perturbative solutions which look exactly like the hydrogen atom solution, equipped with a mode structure, NLM, and a gravitational fine structure constant alpha, formed from the black hole and boson masses. This is what is usually referred to in the superradiance context as the gravitational atom, with the lowest mode cloud around a black hole shown in the illustration here. In the context of the specific case of the axion, we search for evidence of axion-induced superradiance in the GWTC-5 catalog of LVK in this work, which would manifest as black holes spinning down to specific spin values. The LVK catalog is the most extensive gravitational wave inferred binary black hole catalog to date, with over 250 binary black hole events recorded. This is in comparison to, for example, around 45 or so in the last superradiance-based search of this type in 2021 using GWTC2. The search can be roughly conceptualized as follows. Shown here is what is known as Regge plane. We illustrate the black hole spins and masses with error bars from LVK parameter estimates, as well as the saturation spin curves, which are the expected spin down values for a given black hole type for a certain axion mass and merger time, assuming superradiance occurs. Events along the curve would suggest that superradiance spins a black hole down to that value, giving evidence for a certain axion mass. Events far above the curves would suggest evidence against superradiance, as you would have expected black holes to spin down. This helps visualize the type of search we're doing in this work with the GWTC-5 events. Quantitatively, we use hierarchical likelihood methods to infer evidence for axions from the GWTC catalog parameter estimates, that is, the mass and spin measurements of each event with uncertainties. This procedure involves sets of hyperparameters, namely the parameterization of the natal black hole spin distribution, as well as the merger times for each binary black hole event. We incorporate the GWTC parameter estimates into this likelihood, and one can derive a marginalized posterior on the axion mass, shown here for GWTC 3, 4, and 5. From the obvious posterior dip structure, one can then infer an exclusion on the axion mass, which tells us where the data shows no evidence for axion-induced superradiance. Of course, we also examine a variety of other systematic uncertainties in our paper, such as the distributions of natal spins and merger times, as well as the prior used for the axion mass, for example. In conclusion, we find no evidence for axion superradiance in the latest GWTC-5 catalog of LVK, which is the most extensive binary black hole catalog to date. This sets exciting new constraints on the axion, for which we focus on the QCD axion case throughout. This search is highly complementary to existing superradiance searches, which are often based on X-ray spin measurements with various systematic uncertainties. Looking forward, it would be exciting to extend these binary black hole superradiance searches with the next round of data from LVK-04C, and then later on more events will be obtained with LVK-05 after that, and then third generation gravitational wave observatories after that, giving us unprecedented sensitivity to the binary black hole events within our observable universe, which can then all be used to further our search for axions. Thanks for listening, and we hope you check out our paper.